Thank you, everybody, for being present or listening to this talk. I want to thank the organizer for inviting me. It's a good opportunity. I'm very happy to be here, and I will try my best to do an introduction to EPR and how I use it to understand and improve magic angle spinning dynamic nuclear polarization. So maybe the first thing is I thought I should maybe introduce myself. So I come from a material science, physical chemistry background, where during my PhD, I did a lot of single crystal synthesis and single crystal analysis with EPR and NDOR of paramagnetic species. In particular, we looked at this titanium doped gallium oxide and understanding how the quadrupolar interaction is, understanding how the relaxation times works in this system with the idea of quantum computing. So this is basically something called a spin bus. And that's how I got introduced to many aspects of EPR. And later on, I did high field EPR with this training and DNP. And that was at Weizmann Institute, but my PhD was in Paris 6. And there I became really interested into the MAS-DNP theory with Shimon Vega. And that led me to work at CEA with Gail de Pape and apply the EPR and the theory of DNP to understand how DNP works under magic angle spin. And I carried on this work as I joined the Mag Lab. So it's been a busy week for me. This is what we had last week. I'm no exception to many researchers. We all have deadlines. And unfortunately, this threw down the drain 4 days of my work. And the talk does not look exactly how I wanted it to be, but I hope you will be able to understand. If I forgot to acknowledge somebody, please forgive me. I did my best, the best I could in the amount of time I had. So let me start. An electron or nuclear spin in the magnetic field, as you know, will interact with it, and you will have, if it's a spin 1/2, 2 energy level, and one will be a stable level and an unstable level. So this depends on the thermal energy of the system. So if its energy difference is small compared to the thermal energy, then basically you have equal population if you look at the statistical assembly of spins in the lower state or the higher state. This is actually the case in many NMR experiments. And the consequence is that if you look at protons in liquid state, often the signals are of low intensity, and therefore the signal to noise ratio are low. Another consequence is also you have weaker, slower relaxation times, and therefore recycling delays tend to be longer. You have the other case where the difference in energy is greater, or at least of the same order of magnitude as the thermal energy. And in that case, you have more spins in the lower state as compared to the higher state. And this is routine in a high field EPR and low temperature. And in best of the worlds, you would like to have this situation of strong polarization and large signals combined with the amazing resolution NMR gives. And that's basically the idea behind dynamic nuclear polarization, is to combine the best of both worlds. So MAS-DNP is basically magic angle spinning and DNP combined together. And that has really enabled a plethora of experiments that were previously impossible. We can now look at samples with nuclear spins at very low concentration. And the way most of us do it is using what I call the Griffin's design, where you use a gyrotron to generate the microwave. You cool your sample at about 100 Kelvin and you spin it at this temperature. And you also use the biradicals, that also comes from Griffin's design in a way, to generate the nuclear hyperpolarization. And the advantage of these biradicals is that they generate cross effect, which in a sense creates very quickly the nuclear spin hyperpolarization. And so far, can be wrong, but cross effect provides the best sensitivity per unit time and the best high field performance. Of course, not everything is great. DNP is not always efficient. especially at very high field, and we are still very far from any theoretical limits when it comes to hyperpolarization. There are obvious solutions that one can think about is to improve the hardware, for instance, the microwave sources of providing better beams, probes that are more sensitive, guide the microwave better. You can think about helium spinning, which enables to lower the temperature and further improve the sensitivity. And you can also think about alternative methods like Pearl's DNP method that in principle are field independent. You can also think about making better biradicals. This is what or using different polarizing agents, different mechanisms. So you could use metal centers or intrinsic radicals. As far as I'm concerned, I'm interested into improving biradicals. This is something that I'm really keen on. And there are basically two families of biradicals, the homobiradicals, where the two moieties have roughly the same G tensor, so the same interactions with the magnetic field, or the heterobiradicals, where it's a different G tensor for the two moieties. There's a lot of development on the biradicals. There is no ideal biradical. Actually, I think that ideal biradical is pointless. It may be field dependent. So some biradicals will be better at certain field than others. And clearly, every time you make a new biradical, the EPR input is needed. So among the questions, how is the radicals properties impacting the DNP? And how can we, for instance, use EPR to determine the biradical geometry? Because it's one thing to make a molecule, it's another thing to know how its 3D structure is. So EPR stands for Electron Paramagnetic Resonance. You may also know it under the names of electron spin resonance, electron magnetic resonance. These are the same thing. And DNP is the middleman between the EPR and the NMR world. And because it's the middleman, actually most of the early DNP setups had both EPR and NMR capabilities. And I just showed here the example of Schlichter, Wind, and Iannoni, where you had an instrument that could combine DNP and EPR. And in particular, and I find this amazing, is the work where you have magic angle spinning and EPR at the same time. The reason why it's interesting is also because the pioneers valued the EPR insights that were provided by these setups. But today it's challenging to have the same equivalent because the high field EPR is challenging, as I'm going to mention. So EPR and NMR are equivalent. The difference is the strength of interaction with the magnetic field or the coupling. It's 658 times stronger for an electron spin as compared to a proton. So instead of talking about megahertz, we talk about gigahertz for a given magnetic field. The other thing is that the electron spins are not isolated. They are within a bond, and they are within bonds, and therefore they are affected by the orbital angular momentum. And in particular, when you talk about the G tensor, you always need to think about there is always some contamination due to the orbital angular momentum. The stronger couplings the stronger interactions means you have stronger couplings. We are not talking hertz and kilohertz like in NMR. We're talking about hundreds of kilohertz to megahertz. And as said, the electron spins are sensitive to orbital overlap. And one interaction, for instance, is the exchange interaction, which is a nascent bond. And finally, stronger interactions means also faster relaxations in general. So this is a scale where if you have the electron T2s and the electron T1s as compared to the nuclear T2s and nuclear T1s, you can see those are almost two different worlds. Now let's talk about the magnetic interactions of an electron spin. So basically, I'm going to focus on organic biradicals. So the main one is the G tensor. It's the equivalent of a chemical shift in NMR, where you have both the isotropic and anisotropic component. And this anisotropy arises from the presence of some orbital angular momentum. And you have, for instance, in the case of nitroxide, a larger span because you have both an oxygen and a nitrogen, while in the BDPA, where you only have carbons, the span of the G tensor is smaller. So this impacts the NMR, the EPR line width. And in the case of tritium, this is an example at high field, where the line shape is mostly determined by the G tensor. Now you also have a dipolar and exchange interaction, which are the interactions between electron spin. That would be the equivalent of the homonuclear dipolar and J coupling. So it's through space for dipolar coupling, but there can be some effect of the orbital angular momentum. Typically for biradicals, it's of the order of tens of megahertz. And you have also the exchange interaction, which is basically the overlap between two orbitals, or the beginning of the overlap between two orbitals. Typically for biradicals, this is between 0 and 100 megahertz in absolute value. And this would be the relevant Hamiltonians, I forgot to say, for these interactions. And finally, the most important one for DNP, in my opinion, is the hyperfine coupling, because this is the one that allows the talking between the electron spin and the nuclear spins. And in particular, one critical term is what we call pseudo-secular term, where basically the quantification axis of the nuclear spin is slightly tilted by the presence of an anisotropic hyperfine coupling. Again, through space, some angular orbital momentum. I forgot to mention, you also have isotropic component on this one. For the DNP process that I'm mentioning today, it's not the most critical one. That would be the isotropic one here. And that would be how the G tensors relate with respect to the molecule. I'm representing here with these ovoids. And the hyperfine couplings gives you an indication of how far apart they can spread out on a molecule, which is AMUPol, one of the most used biradicals so far. There are two flavors of EPR. And for NMR spectroscopy, it's a bit confusing. So we have continuous wave EPR, which would be the very old style NMR. And you have pulsed EPR, which is like the modern NMR. Continuous wave, basically, you have a fixed microwave frequency and you sweep the magnetic field. The advantage of this method is that it does not require a lot of microwave power. It does not really distort the EPR spectra, or at least this gives you the most quantitative approach for the EPR intensity. Experts may disagree with me here, but this is my understanding. It's quantitative, that's another aspect of it, and can be applied therefore at very high field because you only require modest microwave power. The fact that it has limited distortion is very important for the structure determination as far as I'm concerned for the biradicals. If this is what you're used to, an absorption spectrum, under continuous wave CW EPR, you actually need to modulate the field to improve the signal to noise. So basically, the magnetic field is swept, but at the same time modulated. And if you detect synchronously, then you can obtain the derivative of a spectrum if you do it in the right conditions. And this is the most common form of EPR. And I'm sweeping under the rug so many details here. And if you have questions, you can ask me later. And the simplest EPR experiment you can think of is just with a benchtop EPR spectrometer. You can, for DNP, check your radical concentration, check if the sample preparation, track the degradation. See, for instance, we have observed that in cellular milieu, in cell, in fungi, in native biofilms, the radicals tends to degrade. And that can give you an idea on how quickly they degrade. Can also give you some hints about sample preparation. So for instance, the red curve corresponds to a good sample preparation for cellulose. That's a sample from Tuowang. And while the blue is a bad sample preparation. In that case, radical is just more mobile. Understanding exactly why is difficult, but this is actually a good tool to have to gain some insight on sample preparation. And of course, such benchtop EPR spectrometer can be used to low temperature, and you can also have saturation factor. That's when you change microwave power, or you can obtain solid state EPR spectrum, which can be used later for fitting. A less common form of EPR is pulsed EPR. And it's not exactly like pulsed NMR in the sense I would consider it closer to wide-line NMR, because most of the pulses we used in EPR are selective pulses, at least as you go higher in field. Typically, the pulses are between 10 and 10 nanoseconds to 1 microseconds, and that corresponds to roughly megahertz or sub-megahertz nutation frequencies to hundreds of megahertz. To reach those nutation frequencies, you actually need high power. And if amplifiers at 9 to 10 gigahertz are more common, very high frequency amplifiers are scarce and sources are scarce. And as far as I know, we can go up to 395 with solid state sources, but then the pulses are very selective. Selective means that if this is your EPR line, you only excite a very small portion of it. And it turns out that this brings in some complications. For instance, when you excite the spins, they may talk one another, or they may talk with the spin packets that are around. And if you measure, for instance, electron relaxation times as T2, then the selective pulses can make things a little tricky because you have effects of instantaneous diffusion or spectral diffusion. This is this crosstalk that I just mentioned. And to give one example, the instantaneous diffusion is sensitive to the radical concentration. It's sensitive to the angle of the pulses you're using, but also to the EPR intensity at the position you're detecting. And therefore, that can lead sometimes to distortion if you detect a spectrum with an echo field sweep experiment. But a good aspect is that you can also extract the concentration by changing one of those factors and then being able to have a direct quantification of your radical concentration. There's a lot of work about this. I'm mentioning here Arnold Reitzimring because I met him and his work has inspired me. If you're curious, you can read those two papers I'm putting here. There are, of course, many more papers. You can also with pulse EPR measure relaxation times and measure the intrinsic, like the T1 is often contaminated by spectral diffusion. That's this crosstalk between excited and non-excited spins. And inversion recovery, in my opinion, tends to lead to harder to interpret curves. And I prefer to use, for instance, saturation recovery pulse sequence. And in general, if you do those experiments, I would recommend that you work with lower radical concentration. And while this is not exactly the DNP conditions, I believe this enables a better comparison in between biradicals. If available, you could use an arbitrary waveform generator to excite the whole EPR spectra, but this is not common. You have it at X band, at Q band, and now at W band, but there are very few setups that have these capabilities. And when it comes to electron relaxation times, the T1, I recommend the literature by the Eaton and Eaton on the organic radicals because they have measured everything, I believe, and all the conditions possible, various solvents, various temperatures, various fields. And I'm mentioning here a few of the papers if you want to dig in this literature. Finally, I'm not mentioning that there's a plethora of pulse sequences in EPR that are inspired in part by NMR, but are also different from NMR because we are using selective pulses. And this is a book I would also recommend if you want to dig in pulse DPR. This is the one I've been reading a lot during my PhD. And there's also a somewhat free version here. This is not a typo. This is how it's written on the website. So now, there's one last thing I would like to mention is that about EPR is that names are confusing. So you may hear about L band, S band, X band, Q, W, G band. So basically, those corresponds to bands in which the microwave can propagate through the atmosphere, and those corresponds to name that the military was using. And the first MAS-DNP setups were basically using Q band, which was accessible, and you can have sources. Most MAS-DNP instruments operate more in this range or higher frequency. And there are very few places that can do pulse DPR under those conditions. I'm mentioning here Daniel Goldfarb or Thomas Prisner. I could mention David Britt or Song-Gi Han. There are very few groups that can do such experiments. So far, I know that 395 is possible at the Mag Lab or within Ilya Kaminka's group. The reason there are not so many possibilities because there are not many sources that fits the DNP and also the EPR requirements. Okay, this is now helps me. I can now transition to actually high field DPR and to how I'm using EPR and high-field EPR to understand the DNP, the MAS-DNP in particular. And what was my aim? My aim was to actually have quantitative simulations, and the inputs of EPR is absolutely critical. And I'm putting a disclaimer. I'm just going to talk today about biradicals. There's many work that I could mention, but in the 45 minutes I'm allocated, I'm going to focus on the biradicals. So a biradical is basically a molecule with two unpaired electrons. But you can, and to mimic DNP, you can just assume I have two electron spins and one nuclear spins. And those you will account for the G tensors I mentioned before, the couplings between the two, and then the coupling to the nucleus. If you take a single crystal of this biradical, let's say this would give you the black and blue EPR line. So this would be for each of the radicals if you ignore the coupling. And if you take a powder, that would give this broad pattern. Under static conditions, you would burn a hole into your EPR if you were to do the DNP experiment. It's a little more complex, but we will keep it simple. You just burn a hole. But under MAS, the things are a little more complex because the G tensors are inducing a periodicity in the interactions. So the energy levels are time dependent and periodic. And the consequence is that also the EPR line under irradiation is not a hole burning, it's significantly more complex. And actually, now we can go into this diagram a little more. If we look at these energy level diagrams, there are multiple conditions where the microwave can be on resonance with an electron spin, or you can have a energy level crossings or anti-crossing if I want to be rigorous. So those energy level crossings and anti-crossings on top of on resonance are critical for the DNP. You can look at these energy levels as a fictitious spin 1.5 when they cross. And if we dive into the details, you have a microwave, which is one type of crossing where it will affect the polarization of one of the electrons. And then in the off-diagonal term would just be the microwave power. Then you have the dipolar and exchange interaction. What they tend to do is actually exchange polarization in between the two spins. And in that case, the off-diagonal element would be the dipolar and the exchange interaction. And then you have a cross effect, which is the one which feeds the polarization to the nucleus and basically transfer this polarization difference to the nucleus. In that case, it relies on the hyperfine, the same electron coupling terms, and is inversely proportional to the magnetic field. And basically, those two types of rotor events are what's going to determine the shape of the EPR spectra under irradiation, while the other one is what is going to determine the build-up time that you observe experimentally. So in part, I would say, but this is the main driver. It's a simple model for free spins, but it's already providing a lot of information. For instance, this is what I showed you, and this is what you would observe if you were to do the simulations. You would observe an hyperpolarization. That means a gain of polarization compared to the thermal equilibrium polarization. But if you remove the microwave, there are still energy level crossings occurring. And it turns out that they impact the nuclear polarization. They actually can reduce the nuclear spin hyperpolarization, the nuclear spin hyperpolarization. And that's a phenomenon I call depolarization. It's a reversible mechanism. It should not be really confused with a paramagnetic bleaching. This is really something else. This is reversible. This is only with cross effect. And basically it has an impact, which is when we measure an enhancement, which is the ratio between microwave on and microwave off, and we do this with biradicals, we are not really quantifying how much we are gaining, and we can obtain absurd results. A free spin system gives a lot of insight. We can understand how the dipolar and exchange interaction impact the mass dependence. It can also help understanding how the relative orientations of the biradicals are impacting the efficiency of the DNP experiment, how the DNP field profile would look like. So that means how much enhancement you would get as a function of magnetic field, but it's not quantitative. And to be quantitative, you want to include more spins, but it's a very slow process I think I'm going just to skip what's going on here in the interest of time, but I will just mention what's going on. If you had more spins, then you have more dipolar couplings. You have dipolar couplings occurring in between radicals, and you have dipolar couplings occurring in between protons. And those additional dipolar couplings will induce new dipolar rotor events that you need to factor in to the simulations. So using an approach where I use fictitious spin 1/2 and something called Landau-Zinner approximation and applying it in Liouville space, I managed to get a linear scaling of a problem. And I actually chose to do two types of simulations. One where I have a free spin system in a box, and it's repeated so that it matches concentration of the experiment, and one where I had a biradical surrounded by many solvent molecules. The first one enables to account for the biradical concentration and the aggregation. The second model is good to understand spin diffusion and predict the build-up times. So actually, you can combine these two models if you assume that the cross effect occurring between biradicals is not important. So only the cross effect occurring within one biradical is important, not in between radicals arising from two different biradicals. And this is actually very reasonable when you do the simulations. And as a consequence, you can use the multi-nuclei model and just apply a correction factor obtained by this box model to obtain quantitative simulations. And I mentioned it's equivalent to what Fred Perez did, but it's done in a different approach. And I looked at it from an EPR point of view, actually, when I did this, not an NMR point of view. Now, we can go into the biradical design, and basically the biradical design is the chemical bridge you're going to use, the G-tensors, their orientations, the molecular weight, because it affects the relaxation times, the solubility. And for each of these parameters, there are either an optimum or a happy medium. So it's similar, I would say. There's always an optimum value that you need for each of these components. There is an optimum for this one. That's the maximum you can reach. But for this one, you need a happy medium because you could play. Sample preparation is something else. You want the nuclear spin in your medium to relax as slowly as possible, and that you can control with deuteration by playing with the glass matrix, the temperature, and of course the sample has an impact. But that your sample is your sample, so you can just play around. And this is actually the region where EPR is extremely useful. And let me explain. Like EPR is actually at the center of everything I did. You have the EPR at high field is going to give you a lot of information on what's going on at high field. And you can determine the structure of a radical through EPR using as DFT and MD simulations. The DFT is going to give me the input parameters, and the MD is going to give me the flexibility, an idea of the conformers that the molecule has, and then I can feed the EPR spectra. Once I have the EPR spectra and I have measured the relaxation times, I can also use CST simulations, so that's electromagnetic simulations, to have input for the MAS-DNP simulations, and I can compare with the experiment. And this process is actually a process to determine 21 variables. So this is a lot, and it's easy to fit experimental results with the MAS-DNP simulations, but it's not always meaningful. And this is really where APR is key. And the first application was a simple, quote unquote, application was on two very different radicals, TEKPol and AMUPol. Those two radicals that you have here and here are very different chemically. You can see the bridge is very different. As a consequence, you expect very different magnetic and geometric properties. If you do the DFT on just simpler molecules, so you don't have the rings, this is how the G-tensor would orient for those two molecules and the dipolar vector in between the two. So they are very different. And in that case, you can run EPR at just one field to already see a massive difference that it leads to. You can see that at high field, TEKPol has a different signature in what we call the GX region. You can see this bump here, it's slightly shifted for AMUPol. You can see that this splitting of the nitrogens are actually splitted even further here, which is an indication of strong coupling in between the nitroxide. And you can see also a kink in this transition. And all this is reflects the different magnetic properties. You can now fit the EPR spectra based on the DFT inputs, and you can get a good agreement. You can extract the relative orientations, the dipolar and exchange interactions, but you can also, as mentioned, extract the relaxation times from the experiment. And I mentioned one field was sufficient in that case to obtain the different features. And when I did the MAS-DNP simulation, I could reproduce the trend of a DNP field profile for both radicals. And I could also reproduce the trend of polarization gain, depolarization, epsilon on off. Those are the experiments. Those are the simulations. And also the build-up times could be somewhat reproduced. The agreement was pretty good. There was one fitting factor in that case, two fitting factors, the microwave power, and also the relaxation times of the closed protons. I mean, the ones that are close to the radical. So the method works. And I wanted to go one step further and see how quantitative I could be. I looked at the case of bTurea biradicals. So those biradicals, as I'm showing here, it's AMUPol, bCtol, and bCtol-M, have very similar structure. The bridge in between the two is identical, except the substitution on the nitrogen. The substitution on the ring has a modest impact. We can ignore it for now. But here, it's really this which is changing. And an observation was bCtol was better. Sorry, bCtol-M was better than bCtol. And actually, those substitution create a steric hindrance. And it rigidifies radical and affect the relative orientations of the two rings. If you do the DFT, you immediately see that the substitution is making the ring tilt. So you can see this one is more tilted than this one. You can quantify this using the G-tensor distance, which is a metric that can measure how differently oriented the two radicals are. And the G-tensor distance actually increase with substitution. When you look at the DFT, the dipolar coupling and the exchange interactions are all predicted to be of the same order of magnitude. So this may not be a criteria that explains the difference in the performance. And actually, to really identify the geometry of a radical, I had to use two frequencies, 9 gigahertz and 240 gigahertz. The 9 gigahertz was showing differences in this region. And this is actually important because it was easy to obtain good agreement for the high frequency, but having a good agreement for both was difficult, but necessary to be sure that the structure were correct. You can see so green is bCtol, AMUPol is black, bCtol-M is blue, and the fits are the dashed lines that are overlaid. And you can see that these spectra are also very different at a field. And in particular, you can see that this bump here is shifted towards the GX region, and the bump at the GX region is more intense in the case of bCtol-M. And actually, once I could compare with the DFT prediction, and I could see that the Euler angles of the DFT predictions were reasonable, but you still need to tweak to have a correct geometry. Also note that the exchange interaction I mentioned cannot be extracted here from the liquid state. You really need to do the simulations in the solid state. Once you have those fits, you have all the parameters I mentioned for the DNP simulations, and you can now compare the DNP field profile to the simulations. So again, bCtol, AMUPol, bCtol-M, and the agreement is in general good to very good in between the experiments and the simulations. You can also look at the prediction for announcement and build-up times, and they are in quite good agreement with the experiment. And one thing I can summarize is that the reason bCtol M is better is because of the relative orientation. And now I'm going to speed up a little bit. This is another example of the AsymPol. This is really one step even further. It's really trying something which is significantly harder. We designed this molecule, AsymPol, and we tweaked it to make it water soluble by adding phosphates. And that's a radical that works very well. However, in my first attempt to fit the EPR spectrum, I miserably failed. I had just one conformer, and this is not a good fit. And once I added rings, we added rings to make this radical better, so to make it heavier, because that increases relaxation times. Then when we did VEPR, they were different. Again, I used TFT and MD simulations, and I could see that there are two conformers, and those two conformers actually have different proportions and different exchange interactions. They have the same dipolar coupling, but they have different relative orientation and different exchange interactions. And for bCtol, for C-AsymPol POC, it is different ratio and different interactions as compared to AsymPol POC. Once you account for this, you can now fit VPR spectra. Actually, the values I showed are extracting from the fit. And now for this is AsymPol POC, and this is C-AsymPol POC, and the agreement between simulations and experiments, simulations in red, is very good. And once again, you can fit the EPR, the DNP field profiles. Okay, another thing that we noticed with this radical, once you have all those parameters, you can start to play around the radicals. We noticed something. We noticed that if we are working in a deuterated media, the radical of AsymPol POC and C-AsymPol POC were somewhat better than AMUPol, but not significantly. However, when going to protonated media, the enhancement went up, and it was working better, significantly better. It's odd because AMUPol is known to work not well when the proton concentration is high, but AsymPol worked better. With the TFT and MD simulations and EPR fits, you can predict the enhancement, the build-up times, and the simulation works. So you can go one step further and see, okay, what's happening around those radicals? Because if deuteration is affecting the DNP, there is something to dig. I will go quickly. You can, as mentioned, you can do the simulation and look around how the spin diffusion works around the radical now. And this is how the polarization builds up around the biradicals. So in white, those are the protons on the molecule, black, the protons around the molecule. And you can start to do in silico deuteration. And if you do in silico deuteration, you do realize that this has almost no impact. While AMUPol would be affected, AsymPol is not. And when you do the experiment, oh, it's a typo. This should be AsymPol here and here. So you can see, you can do experiments. We could not completely deuterate the radical. We only partially deuterated it, but we could get a good agreement between experiments and simulations. And last example is, you would assume that turning the AsymPol for organic solvent would not impact so much the structure, but it actually does. You can observe it in the EPR spectrum. And this was, again, needed to understand the DNP field profile for those two radicals and being able to have more quantitative simulations. There are things I did not talk about during this talk, which is other applications of EPR. Is, for instance, the Eldor experiment, which has been used, for instance, by Goldfarb Group and Songhi-Han to understand how DNP works under static conditions and how would look like the EPR spectra under irradiation. And I put some references for those who are curious about the mechanisms behind. Another thing I did not mention is, while I showcased how I did the fits using DFT and MD simulations as inputs, there are other groups that have done very good work at fitting the EPR spectra, for instance, Prisner for BTBK, or Griffin and Matthias, where they used simulating annealing to obtain here. So this is the work by Matthias et al., where you have the fits of different biradicals at different fields, and you can see the agreement is amazing. I'll be honest, I have tried this method, I failed. So congratulations for those who have been successful. Finally, I could also mention the work by Prisner, where he looked at the temperature, Prisner, Oshkinat, and Sigurdsson, where they looked at the effect of temperature on the relaxation times to understand how DNP is affected at high temperature. I could also mention how you can use EPR to understand more mobile electrons. And this is an example I worked on where I looked at conductive polymers, but in the interest of time, I will stop here. So in conclusion, we have two flavors of EPR, continuous wave and pulsed EPR. And the continuous wave is what you most likely will encounter into a chemistry lab or chemistry department. It's very useful to know if your sample preparation is good. It's good to know if your radical is stable. It's quantitative, so you can compare different preparations and see if you consistently get the same concentration, for instance. And as far as I'm concerned, I like it because it has limited distortion and can work to very high fields, which for me is essential to determine the biradical structure. Now you have also the pulsed EPR. It's less common, unfortunately. But it's obviously necessary if you need to know the spin dynamic properties. And there are only very few not very few, there are few high fields EPR setups because the technical requirement on the source is very demanding. So W band so that's 95 gigahertz, 3.3 Tesla, roughly speaking, are becoming a little more common, but you won't find them everywhere. There are improvements at higher frequency in the 250 to 260 gigahertz with TWT amplifiers. And I'm giving a reference for those who are curious about the capabilities. And so far, if you want to work at very high field, like 14 Tesla, which are the conditions at which we do DNP, then we are limited with solid state sources and therefore very selective pulses and all the drawbacks that comes with it. Also, while I talked a lot about EPR, I never showed any of the DNP setups I worked on. So those are pictures of the setups I've used, starting from X-band to W-band with Daniela Goldfarb and Shimon Vega. The pulsed EPR when I was a PhD student, and now the pulsed EPR I'm using with Hans van Tol, or even this EMX Nano that I'm using for CW experiments at the MagLab and check the DNP samples when I'm running experiments. And I showed you examples of applications of a combination of EPR and DNP to understand how the DNP mechanism works, but also what parameters affect the DNP. I showed it on TEKPol and AMUPol, two, I would say, quote unquote, easy case, though not so straightforward. I showed it on a more subtle case, which are the bTureas, where we were just looking at small variations in the chemical structure and how these were impacting the DNP and how they were impacting the structure. And I would say, I should have said, how they were impacting the structure and therefore how they were impacting the DNP and the performance. And in particular, this is clearly an indication that the relative orientation was so critical in the changes here, not really the change in the couplings between the electron spins. Another example was on the AsymPol, where EPR helped me figure out that there are two conformers, and this is the only way those EPR spectra could be fitted correctly. And knowing the fact that you have two conformers is also an indication that actually this one is not a great MAS-DNP performer, while this one is the one I would like. So this means that as I want to get strong couplings between the biradicals, this is becoming very critical. The conformers are becoming extremely critical. And I showed a toy application where basically if you deuterate the radical, then nothing happens in the case of AsymPol Cook, unlike in the case of AMUPol. And while DFT and MD is guiding the design of molecules, I have multiple candidate molecules, EPR is still critical. It is really the method that sends me back to the drawing board and helped me figure out, oh, I forgot that. Now, I showed quantitative simulations, ignore this. And I would like to thank the people who have been working a lot on this project. So the Vegas group, Anil, Seth Jackie, Thomas Albriter, Snorri Sigurdsson, Faith, my postdoc, who has been really helpful for all this, Hans Van Tol, and the TEPAP group, where this was roughly, well, almost everything was started. And I also would like to give an acknowledgement to the people that trained me to EPR. So this is Laurent Binet, he was my PhD advisor, Didier Gourrier and Hervé Vezin, that were co-advisor during my PhD and from whom I learned CW, EPR, and Endor, and also Pulsed EPR, Pulsed Endor. And Daniela Goldfarb, of course, who really trained me for high-field EPR. And with that, I can also thank the sponsors for this research. And if you have questions, I will be more than happy to answer them. Thank you.
Thank you very much, Fred, for that excellent talk. For people in the audience, please enter your questions in the Q&A for Fred, and he'll take some time now to answer those questions. So I'd like to start with a question. It was very interesting to see the results about deuteration and how that affected DNP. So did you look at different proton deuterium ratios at all, or do you have some work on that?
So do you mean like solvent deuteration as and the performance? I have never done anything systematic. There's a paper, if you want, I can share later. I can share you a paper where they did something more systematic than what I did. Most of the time, the reason I have not done it is because if you use membrane proteins, for instance, deuteration is expensive, and that you often end up having to use fully protonated media in that case. So I just looked at the two extremes to see, okay, these are basically the two conditions, the ideal conditions where everything is deuterated and we have a good control, and the more realistic case where it's a mess and you have lots of protons. But I will share a paper if you want later.
Thank you. Yes. So we have a question from Zhao Peng in the chat. Zhao asks, could you comment on the bad sample preparation and what to keep in mind to avoid for bad sample preparation?
Okay, there are different aspects. First, you can know what's your actual radical concentration. So it gives you an idea of if you have enough proton to radical ratio in your sample. So if you have a very weak SNR in your EPR, most likely you don't have enough radical in your medium to carry out good DNP. Now you can look also at the mobility of a radical. In the cellulose example I showed, it appears that when the radical is a little stuck, in other words, it's not as mobile, so the lines are less narrow, then the enhancement is lower, and the enhancement on the sample is lower. I think this is due to a change in the local dynamics, so the glass formation is not as good once you freeze it, when you have this type of behavior. There's also an obvious case, which is radical aggregation. So you don't see any features anymore. You just see a blob and everything has collapsed into a single line. Then you know something is really wrong here.
Thank you.
Did I answer? Yeah.
I think that answers the question. We have a comment in the chat from Jeffrey Bodenhausen, who says, amazing how much information you can pack into 45 minutes without losing your audience. Outstanding. And I'd like to second that. This was a great information-dense seminar. Thank you.
Yeah, I think it's dense. I'm sorry if it's too dense for some, but thank you. Thank you, Jeffrey, for this comment. I really appreciate it. So, well, Wenqing Zhao.
Yes, a question for Wenqing Zhao. Hi, Fred. Or if you want to go ahead and read it, could you give more details? AMUPol performs better at large protonation. Is that I believe that's
I think that's what's meant here. It depends how rigorous you want me to be for that question. I would say I can hand wave the explanation here. Basically, the AsymPol POC, the polarization can go immediately from the nitroxide to the solvent outside. And in that case, you don't need to relay through the protons on the molecule, and meaning that the polarization transfer is faster outside than through the spin diffusion inside to outside. As a consequence, even if you have many protons around your molecule, then you have many pathways for this polarization to get out. And so you can really hyperpolarize easily what's outside. So the cross effect becomes a vastly dominant mechanism for feeding the hyperpolarization and not the spin diffusion. Large proton concentration will then mean more cross effect locally and more overall polarization that can be given to the rest of the sample. Of course, there's a drawback. The more protons you have in your medium, the more your radicals need to supply polarization. So there must be an optimum, but as mentioned, I have not really looked at it. You mentioned that it's possible to pass the limit of 658. Yes, it is possible. So there's a paper, it's the one by Eric Boulot, where basically when you do helium spinning, what happens is as you cool down, the off signal can go, because of depolarization, the off signal can go very low. And when you do the ratio between the off signal and the off signal, this can go beyond 658. Of course, this is not how much you gain. You can't really go past 658 compared to Boltzmann equilibrium. It's because your reference is not Boltzmann equilibrium. Hand wavy explanation is spinning the sample is like warming up the nuclear spins. And the cross effect acts like a heater.
Great, thank you. I have a question from Asif, who just following up on that, the protonation question. So does the fact that there are a lot more protons around lead to faster relaxation of the radicals? And do you have to worry about that in calculations?
So my understanding is the proton will affect the T2 of the electron, not the T1. So I am not concerned about the change in the T1 because of protonation. If I'm super rigorous, I would say maybe deuteration would change slightly the phonon modes and therefore affect a little bit the relaxation. But to the zeroth order, I would say it's not affecting. It's affecting the T2. And as long as T2 is much longer than the rotor events, so how the duration of the interactions between the energy levels, then it's not an issue. At least in the simulations I carried out, the way the T2 is introduced, it does not affect the T2. Sorry, it does not affect the enhancement. The T2 is not very critical here.
Great. I have a question from Alexandre. You mentioned that the enhancement is not exactly how much we gain, but that it depends on the temperature. So this is this ratio you're talking about. So is it possible to correct and calculate the exact gain we have with MAS-DNP?
Yes, yes. But I would have now having done these experiments and they are painful. I would just recommend to compare the signal to noise you obtain for the optimal recycling delay in between biradicals if you really want to be sure of which one is the best. So you make identical samples, you just replace your radical, and you can compare the signal to noise ratio for each of the experiments. This is, in my opinion, the appropriate way of looking at the sensitivity gain. To be honest, depolarization and gain is more like a theoretician point of view. It's more like, oh, I want to dig into the weeds and understand what's going on. The SNR is what you care as an experimentalist. Then there's a question by Gabriele.
Gabrielle asks, in one of your slides, you show no difference in one of your biradicals upon deuteration. If I'm not mistaken, are you not preventing it to escape? So this is another question
Um,
about the duration of the.
wait. So no, actually, so if you titrate your molecule, you can actually hyperpolarize outside. So among details I'm not mentioning is that, for instance, nitroxides tend to form hydrogen bonding with the surrounding water molecules or the glycerol, and therefore you have actually you can have a dense proton network around the radical, and it's just the dipolar hyperfine coupling which is going to mediate here the hyperpolarization. So when you titrate, you basically kill you in principle remove all the protons that are relaxing quickly by removing them from the molecule. And you're not preventing vaporization to escape. You are, if you have a weak coupling between the nitroxides, then this hyperpolarization transfer to the outer world is now more challenging because the rate at which they occur is slower. I've not showed these details, but I've not so long ago I published a paper about it.
Great. So I have a question about spinning. So does the spinning speed affect the accuracy of the calculations if you're looking at very fast or very slow spinning?
Uh, I, I don't know. I answer bluntly. I don't know. For everything I can access to is up to 12 kilohertz so far. I will have a probe that spins faster, and in a few months I will be able to tell you if it's messed up or not. Now I have some hints that the simulations are still good at least to 40 kilohertz. If you ask me beyond this, I am not sure. It all depends on the changes in spin diffusion. And that I'm not sure about.
Great. Have you done any simulations with more than two strongly coupled spins? So looking at triradicals or other systems like that?
No, I have not. So you're thinking about, is it Dotopa? Am I correct on the name, Dototapol? Yeah.
Yes.
I have not tried. One reason is that I have not tried is that it's kind of flexible and I'm not sure what I will be doing and if I can extract anything meaningful. As a side note, yes, I designed one biradical with one triradical where things were rigid enough. And actually, triradical was worse than the biradical because the weak coupling in between, so you had two strongly coupled and two weakly coupled. And this weak coupling messed up everything. So it was better to have a biradical where everything is under control than having a third one, which is almost like a aggregation effect of the radicals.
Interesting. Okay.
Now for the Dototapol, I told you I'm just not I'm just concerned of the input I would place in.
Sure. Yeah. It's a flexible molecule, definitely.
But it works. Definitely. You have proofs.
When you carry out these at a range of different temperatures, are they at the temperatures that the experiments were done, or do you do simulations at certain temperatures and then extrapolate to other temperatures?
So I did simulations at different temperatures so long as I know the electron relaxation times as a function of temperature. Then the code can do it. The code will break down the moment we will go to very strong polarization regime. So when 1 minus PE square will not be negligible in the relaxation. So when you have really an asymmetry between the up and the down relaxation. So then in this non-linear case, I don't know. But for the rest, yeah, you can do simulations roughly between 30 to 200 Kelvin as long as I have the right parameters. It's just a tool.
Thank you. Let's see. Are there any more questions? Do people have questions that they want to enter into the Q&A? I have a question from Asif. He says, DNP experiments are typically performed at high magnetic fields and under magic angle spinnings, whereas EPR measurements used at low field under static conditions. Can you comment on the importance of achieving EPR under the exact same conditions as used in DNP?
Oh, this is a very good question, Asif. In an ideal world, I would love to have a setup that can do EPR and DNP under the same conditions, because not only we would have more accurate values for simulations, but we could also debug immediately the sample in situ. You could just pause on it, look at the EPR and be like, ah, okay, this is not working for that reason, or have at least some clue. Okay, now I do not think the electron relaxation times will be affected by the spinning, and therefore I tend to think that the static EPR at high field would be good. When it comes to nitroxide, whether you measure at 100 Kelvin, whether you measure at X band to very high field, the only thing you will see is an anisotropy in the T1, but I would say the average value is the same across field because the relaxation mechanism behind is the same and is field independent. Now, this is true at 100 Kelvin. When you will go very high field, and even at 100 Kelvin, then other mechanisms may start to kick in particular one called the direct process, and then really having the high field EPR setup at the exact same conditions, static, not necessarily spinning, would really be required to understand what's going on. So if you think 1.2 gigahertz DNP setups, I think we will start to have problems of relaxation times of the electrons in this range.